Part 1: The Paradox. God does not play dice. Albert Einstein said that. It is perhaps the most famous quote in the history of science. But he wasn't talking about religion. He was talking about the universe. He was talking about a specific fear that reality, at its deepest level, was broken. To understand why, I want you to imagine a scenario. Imagine two coins. You take one, and you board a spaceship. You fly to the very edge of the observable universe, 46 billion light-years away. I keep the other coin right here on Earth. Now, according to the strange laws of quantum mechanics, before we look at these coins, they aren't heads or tails. They are spinning. But they aren't just spinning, they are in a state of superposition. They exist in a ghostly limbo where they are both heads and tails at the same time. But here is the magic trick. These two coins are entangled. They share a secret, invisible connection. The moment, the exact nanosecond, I slap my hand down on my coin here on Earth, and reveal it to be heads instantly. Across the entire universe, 46 billion light-years away, your coin forces itself to become tails. No signal passed between us. No radio wave, no beam of light could travel that distance. It happened instantly. It happened faster than the speed of light. Albert Einstein hated this idea. He called it spooky action at a distance. He went to his grave believing it was impossible. He thought it was a glitch in the math, a mistake in our understanding of reality. He spent the last 30 years of his life trying to prove that the universe made sense. But he was wrong. And the truth is far stranger, and far more terrifying, than he could have ever imagined. This is the story of how the universe is actually broken. This is the story of quantum entanglement. Chapter 1: The Clash of Titans. To understand entanglement, we have to go back to the moment physics broke in two. The year is 1927. The place, the Hotel Metropole in Brussels. The Solvay Conference. There is a photograph from this conference that is often called the most intelligent photograph ever taken. Of the 29 attendees, 17 were, or would become, Nobel Prize winners. You have Marie Curie, Erwin Schrödinger, Werner Heisenberg. But beneath the polite smiles and the formal suits, a philosophical war was raging. On one side, you had the old guard, led by Albert Einstein. Einstein was a realist. He believed in a universe of certainty. He believed that objects have real, definite properties whether you look at them or not. If a tree falls in a forest and no one is there to hear it, it makes a sound. Period. On the other side, you had the quantum revolutionaries, led by the Danish physicist Niels Bohr. They were proposing something that sounded insane. They argued that reality does not exist until you measure it. They claimed that until you look at a particle, it doesn't have a position. It doesn't have a speed. It is just a haze of probability. This drove Einstein crazy. He felt that Bohr was turning physics into mysticism. Voice of Abraham Pies quoting Einstein. I recall that during one walk, Einstein suddenly stopped, turned to me, and asked whether I really believed that the moon exists only when I look at it. It sounds like a joke, but Einstein was deadly serious. If Bohr was right, the universe wasn't built on solid ground, it was built on chance. On chaos. For nearly a decade, this debate consumed physics. It was a gentleman's duel. Every morning at breakfast during these conferences, Einstein would present a complex thought experiment, a paradox designed to break quantum theory. He would say, look, if your theory is right, then this impossible thing must happen. The room would go silent. Bohr would look worried. He would spend the entire day pacing, muttering, smoking his pipe, trying to find the flaw in Einstein's logic. And by dinner time, Bohr would have solved it. He would prove that Einstein was wrong, and quantum theory stood firm. Einstein was losing the war. He needed a weapon. He needed an argument so strong, so undeniable, that it would shatter Niels Bohr's probability universe once and for all. In 1935, he found it. He realized that quantum mechanics implied something so ridiculous, so magical, that it had to be wrong. He teamed up with two younger physicists, Boris Podolsky and Nathan Rosen, to write a paper. It became known as the EPR Paradox. And the core of that paradox, it was entanglement. Chapter 2: The Quantum Toolkit and the Gloves. To understand Einstein's argument, we need to understand the difference between the classical world that Einstein loved, and the quantum world he hated. And the best way to do that is with a pair of gloves. This is the essence of the EPR paradox. It is surprisingly simple, yet it holds the key to the deepest mystery in physics. Imagine I have a pair of gloves. A left glove and a right glove. I place them into two identical boxes. I shake them up so I don't know which is which. Then, I mail one box to a friend in New York, and I mail the other box to a friend in Tokyo. A few days later, my friend in New York opens his box. He sees a left glove. In that exact instant, what does he know about the box in Tokyo? He knows with 100% certainty that the box in Tokyo contains the right glove. Now, ask yourself, was there any magic here? Did the glove in New York send a faster than light radio signal to the glove in Tokyo saying, "Hey, I'm being looked at, and I'm a left glove, so you better turn into a right glove"? Of course not. The gloves were always left and right. From the moment I packed them in the boxes, their destiny was set. The information was physically inside the box the entire time. It traveled at the speed of the airplane. Nothing exceeded the speed of light. This is what Einstein called hidden variables. He believed that particles, like electrons or photons, are just like those gloves. They contain hidden instructions. Even if we can't see them, the particles know what they are. But Niels Bohr and the quantum mechanics interpretation said no. You are wrong, particles are not gloves. According to the math of quantum mechanics, until you open the box, the electron inside is not spin up or spin down. It is not left or right. It is both. It is a superposition. It is a wave of probability that hasn't crashed onto the shore of reality yet. And this is where Einstein trapped them. He said, "Okay, Bohr. Let's assume you are right. Let's assume the particles have no defined state until they are measured. If I take two entangled particles, two particles created from the same energy source, and I separate them across the galaxy. According to you, Bohr, neither of them has decided what to be yet. But conservation of momentum tells us they must be opposites. If one is up, the other must be down. So, if I measure particle A here, and it snaps into spin up, then particle B, halfway across the universe, must instantly snap into spin down to balance the equation." Einstein argued that for this to happen, particle A would have to communicate with particle B instantly. Infinite speed. Faster than light. But Einstein's own theory of relativity established the ultimate speed limit of the universe, the speed of light. Nothing communicates faster than light. So, Einstein concluded, there are only two possibilities. Option 1, we live in a world where magic exists, where things communicate instantly across vast distances, spooky action at a distance. Or, option 2, quantum mechanics is incomplete. The particles are just like the gloves. They carried the information with them all along. There is no magic. There is no instant communication. We just don't know how to read the hidden variables yet. Voice of Einstein, I cannot seriously believe in. Because the theory cannot be reconciled with the idea that physics should represent a reality in time and space, free from spooky actions at a distance. It was a masterstroke. Einstein felt he had saved reality. The EPR paper was a direct challenge to the scientific community. It essentially said, come back to us when you have a theory that makes sense. Einstein died in 1955. He died peacefully, confident that one day, these hidden variables would be found. He died believing that God does not play dice. He died without knowing that he had just defined the very thing that would eventually prove him wrong. He didn't know that across the ocean, a young Irish physicist named John Bell was about to pick up that paper and turn Einstein's philosophy into a math equation that could be tested in a lab. And the result of that test would shake the foundations of reality itself. Part 2, the line in the sand. For almost 30 years, the debate between Einstein and Bohr sat collecting dust. It was considered a dead end. Most physicists didn't care. They were busy building nuclear reactors, inventing lasers, and cracking the secrets of the atom using quantum mechanics. The math worked. That was enough. Who cared why it worked? Who cared if it was spooky or not? People started to treat the Einstein-Bohr debate not as physics, but as philosophy. It was like arguing about how many angels can dance on the head of a pin. You can argue about it all night over a beer, but you can never actually test it. Because, by definition, hidden variables are hidden. If you can't see them, you can't measure them, or so everyone thought. Enter John Stuart Bell. Chapter 3. The Unsung Hero. In 1964, John Bell was a quiet, thoughtful physicist working at CERN in Geneva. He wasn't a celebrity like Einstein. He wasn't a loud revolutionary like Bohr. He was essentially a hobbyist of the foundations of reality. By day, he worked on particle accelerators. By night, he obsessively read Einstein's old papers on entanglement. Bell had a secret sympathy for Einstein. He looked at the chaos of quantum mechanics and thought, Einstein must be right. There must be a logical explanation for all of this. He wanted to prove that the gloves theory, the idea of hidden variables, was possible. He wanted to restore sanity to the universe. So, he did something no one else had thought to do. He stopped arguing about philosophy, and he started doing math. He asked a simple question: is there any difference, any measurable difference between a universe where objects have fixed plans, hidden variables, and a universe where they decide instantly, quantum mechanics? At first glance, the answer seems to be no. Remember the gloves. Whether the glove was always left, or whether it decided to be left the moment you looked, the result is the same. You see a left glove. The statistics look identical, 50-50. But Bell looked deeper. He realized that if you change the way you look at the particles, if you don't just ask, are you left or right, but you start asking more complex questions, asking them from different angles, something strange happens. He discovered that Einstein's common sense universe has a limit. A strict mathematical limit. Chapter 4. The Instruction Sheet. To understand Bell's genius, we need to upgrade our analogy. Forget the gloves for a moment. Let's talk about a game show. Imagine we have two players, Alice and Bob. They are our entangled particles. We are going to separate them. Alice goes to Mars. Bob goes to Venus. They cannot communicate. The game works like this: a referee is going to ask each of them a question. There are only three possible questions: question A, question B, and question C. And there are only two possible answers: yes or no. The goal of the game is for Alice and Bob to give the same answer as often as possible. Now, let's look at this from Einstein's perspective, the hidden variable theory. Since Alice and Bob can't talk to each other across space, the only way they can coordinate their answers is to agree on a strategy before they leave. They have to write down a plan. An instruction sheet. For example, they might agree: if we are asked question A, we both say yes. If asked B, we say yes. If asked C, we say no. Let's call this strategy yes, yes, no. Since they have identical instruction sheets, if the referee asks them both question A, they both say yes. Perfect match. If the referee asks them both question B, they both say yes. Perfect match. But here is the catch. The referee doesn't always ask the same question. The referee spins a wheel. Randomly, Alice might get question A, and Bob might get question B. John Bell did the math on this instruction sheet strategy. He calculated every possible combination of plans Alice and Bob could make. Yes, yes, yes. Yes, no, yes. No, no, no. He found something undeniable. No matter what strategy they write down, no matter how clever they are, in a universe based on hidden variables, Alice and Bob can only match their answers a maximum of roughly 67% of the time when the questions are different. Why? Because logic limits them. If a matches B, and B matches C, then a must match C. There is a rigid logic that binds their answers. This limit, this 67% ceiling, is what we call Bell's inequality. It is a line in the sand. Bell essentially said if Einstein is right, and the universe makes sense, then the correlation between particles can never cross this line. It is mathematically impossible. Chapter 5. Crossing the line. Then, John Bell looked at the equations of quantum mechanics. He calculated what would happen if Alice and Bob didn't have an instruction sheet. What if they were truly quantum entangled? In the quantum scenario, they don't have a plan. They don't know what they will answer until they are asked. But, the moment Alice answers, Bob feels it, and adjusts his answer instantly. Bell crunched the numbers using quantum wave functions. And he saw something shocking. Quantum mechanics predicted that Alice and Bob could agree not 67% of the time but up to 85% of the time. This was the smoking gun. Do you see what happened? Einstein's world has a limit 67%. Quantum mechanics predicts 85%. 85 is bigger than 67. This meant the debate was no longer philosophy. It was experimental science. If you could build a machine that shoots entangled photons at detectors set to different angles, question A, B, and C, you could simply count the matches. If the answer is less than 67%, Einstein is right. The world is local, reality is real. The weirdness is just an illusion. But if the answer is higher than 67%, if it breaks the limit, then Einstein is wrong. The hidden variables do not exist. The particles are not carrying instruction sheets. They are communicating. Spookily. Instantly. Bell published his paper in 1964. It was titled On the Einstein-Podolsky-Rosen Paradox. It is one of the most important papers in the history of physics. And you know what happened when he published it? Nothing. Absolutely nothing. The paper was published in a small, obscure journal. For years almost nobody read it. The physics world was too busy with other things. Bell continued his day job at CERN, and his revolutionary discovery lay dormant. It sat there, like a ticking time bomb, waiting for someone crazy enough to try and build the machine. Waiting for someone to actually put the universe to the test. It would take a chaotic, hippie physicist in California, and a meticulous perfectionist in France, to finally light the fuse. They were about to perform the most difficult experiment in history. They were going to ask the universe, are you real? And the answer they got would terrify them. Part 3: The Death of Realism. The year was 1972. The place Berkeley, California. While the rest of the world was distracted by the Vietnam War and the Watergate scandal, a young physicist named John Clauser was creeping into a basement laboratory at the University of California. Clauser was a bit of a rebel. In those days, asking questions about the meaning of quantum mechanics was considered career suicide. Professors would tell students shut up and calculate. But Clauser had found John Bell's forgotten paper. And it haunted him. He wanted to know the truth. He wanted to know if Einstein was right. So, with almost no budget, using scavenged parts and duct tape, he built a machine. It was a clunky contraption designed to fire entangled photons at 2 detectors. Clauser actually hoped to prove Einstein right. He wanted to see the results stay below that 67% limit. He wanted to save the sensible universe. He turned the machine on. He collected the data on punch cards. He ran the numbers, and his heart sank. The correlation was way too high. It broke the limit. The universe was screaming at him, Einstein is wrong. But there was a problem, a loophole. Critics argued that Clauser's detectors were static. They were set in place before the photons were fired. Maybe, just maybe, the particles knew how the detectors were set ahead of time. Maybe the hidden variables were just cheating. To truly kill Einstein's dream, someone had to build a machine that was faster than the photons themselves. Chapter 6: The Impossible Experiment. It took 10 years for technology to catch up. In the early 1980s, in Paris, a French physicist named Alain Aspect took on the challenge. He built an experiment that was a masterpiece of engineering. Aspect's goal was to change the question after the photons had already left the source, but before they arrived at the detectors. Think about how fast that has to be. Light travels 7 times around the Earth in 1 second. In the few nanoseconds it takes for the photons to fly across the lab, Aspect's machine had to randomly switch the angle of the detectors. This meant the particles couldn't possibly know the plan in advance. There was no plan. The plan was being made in mid-flight. If the particles still matched up perfectly, it would prove that they were communicating instantly across space. Aspect ran the experiment. The tension in the physics community was palpable. This was the final showdown. The results came in. They violated Bell's inequality by 5 standard deviations. 5 standard deviations. In physics, that is a slam dunk. That is a certainty. Einstein's hidden variables were dead. Alain Aspect, John Clauser, and later Anton Zeilinger proved definitively that the universe is non-local. This means that space, the distance between things, is not what we think it is. We think that for A to affect B, something must travel from A to B. But entanglement shows us that on a fundamental level, I and B are the same thing. Distance is an illusion. In 2022, nearly a century after the debate began, Clauser, Aspect, and Zeilinger were jointly awarded the Nobel Prize in Physics. The war was over. Einstein lost. Chapter 7: The Faster-than-Light Trap. Now, you might be thinking, wait a minute. If these particles communicate instantly faster than light, doesn't that mean we can send messages faster than light? Couldn't we build a quantum telephone to talk to astronauts on Mars with zero delay? Couldn't we send stock market tips from New York to Tokyo instantly? This is the most common question in quantum physics, and the answer is the cruelest joke the universe has ever played on us. The answer is no. We absolutely cannot use entanglement to send information faster than light. Why? Because nature has a safeguard. A lock that prevents us from breaking causality. Let's go back to our friends, Alice and Bob. Alice is on Earth, Bob is on Mars. They each have an entangled coin. Alice wants to send a message to Bob. She wants to send a 1 heads or a 0 tails. She looks at her coin. It's heads. Great, she knows instantly that Bob's coin is tails. But here is the problem: Alice cannot force her coin to be heads. Remember, quantum mechanics is random. She has a 50% chance of getting heads, and a 50% chance of getting tails. She has zero control over the outcome. To Bob on Mars, looking at his coin, he just sees a random sequence of flips: tails, heads, tails, tails. It looks like total noise. Random gibberish. Bob has no way of knowing why his coin is showing tails. Is it because Alice saw heads? Or is it just random chance? The only way for them to confirm that their coins are connected is for Alice to pick up a normal, slow, speed of light phone and call Bob. She has to say, "Hey Bob, on flip number 1, I got heads. What did you get?" And Bob says, "Whoa, I got tails. It worked. See the catch?" The correlation is instant, but the verification, the useful information, is limited by the speed of light. It's like having 2 magic books that always show the exact same words on the same page. But the words are written in a language that neither of you can read. You know the books are connected, but you can't use them to write a letter to your friend. Nature allows the universe to be interconnected, but it strictly forbids us from using that connection to cheat time and space. Einstein was wrong about hidden variables, but he was right about one thing: nothing useful travels faster than light. So, if we can't use it for a telephone, is entanglement useless? Just a parlor trick of the universe? Absolutely not. Because while we can't communicate faster than light, we can use this spooky connection to do things that classical computers could never dream of. We are standing on the brink of a new era. An era where we harness this magic to build the ultimate machine. Welcome to the age of the quantum computer. Part 4: The Quantum Future. So, Einstein lost the battle. The universe is spooky. But out of the ashes of his defeat, a new world is being born. We are no longer just observing these ghostly connections, we are starting to control them. Right now, in supercooled laboratories at companies like Google, IBM, and rigorous startups, engineers are building the engine of the 21st century, the quantum computer. Classical computers like the one you are using to watch this video think in bits 1 or 0, heads or tails. But a quantum computer uses qubits. Thanks to superposition and entanglement, a qubit can be 1, 0, and everything in between, all at once. When you entangle these qubits together, they don't just solve problems one by one. They explore all possible solutions simultaneously. A problem that would take a supercomputer 10,000 years to solve, a quantum computer could solve in seconds. New medicines, perfect climate models, artificial intelligence that rivals the human mind. All of these are locked behind the door of entanglement. But there is another application. One that sounds like it was ripped straight out of Star Trek. Chapter 8: Beam Me Up. It is called quantum teleportation. Now, before you get too excited, we are not transporting humans yet. And honestly, after you hear how it works, you might not want to be transported. Remember, we can't send information faster than light. But we can use entanglement to transport the state of a particle from one place to another instantly. Here is the recipe. Alice wants to teleport a photon, let's call it photon X, to Bob. She uses a pair of entangled particles as a bridge. She performs a joint measurement on photon X and her half of the entangled pair. This measurement forces photon X to give up its identity. Its information is effectively destroyed at Alice's end. But, thanks to the spooky connection, that information reappears in Bob's particle. Bob applies a correction, and voila, His particle transforms into an exact, perfect copy of photon X. The original is gone. The copy is born. It is the ultimate philosophical horror story. If we teleported you to Mars, we would have to scan every atom in your body, destroy you on Earth, and rebuild you on Mars using the data. Is the person on Mars really you? Or did you die, and a clone just took your place? Entanglement doesn't answer that question. It just makes it possible. Chapter 9 or equals EPR. We have come a long way. From Einstein's gloves to teleportation. But there is one final twist in this story. A twist that might finally bring peace to Einstein's ghost. For his entire life, Einstein had two children. His favorite child was general relativity, the theory of gravity, curved space, and black holes. His unwanted child was quantum mechanics, the theory of particles and spooky action. These two theories hated each other. They spoke different languages. They refused to work together. But in 2013, two physicists, Juan Maldacena and Leonard Susskind, proposed a radical new idea. An idea that connects the biggest things in the universe with the smallest. It is called ER equals EPR. EPR stands for entanglement Einstein-Podolsky-Rosen. ER stands for Einstein-Rosen bridges, better known as wormholes. You know what a wormhole is? It's a tunnel through spacetime that connects two distant points. A shortcut. Maldacena and Susskind suggested that these two things are actually the same thing. When two particles are entangled, they aren't just communicating by magic. They might be connected by a tiny, microscopic wormhole, a bridge through the fabric of spacetime itself. If this is true, then spooky action isn't spooky at all. The information doesn't travel across the universe faster than light, it takes a shortcut through the universe. It is a poetic irony. Einstein spent years trying to destroy entanglement. But in the end, entanglement might be the very thing that stitches his universe together. Space, time, gravity, and reality might all be sewn together by the invisible threads of quantum entanglement. Conclusion: God does not play dice. Maybe Einstein was wrong about the dice. But he was right about the mystery. We live in a universe that is far more interconnected than we ever dared to dream. We are not isolated islands in a dark ocean. At the fundamental level, the particles that make up your body, the air you breathe, and the stars you see have been dancing together since the Big Bang. We are still just children playing on the seashore, picking up smoother pebbles and prettier shells, while the great ocean of truth lays all undiscovered before us. But with every experiment, with every entangled photon, we are wading a little deeper into the water. If you enjoyed this deep dive into the mysteries of reality, make sure to hit that subscribe button and ring the bell. Here at Quantum Files Official, we don't just scratch the surface, we explore the deepest questions of the universe. What do you think? Is the universe truly random? Or is there a deeper order we just can't see yet? And would you step into a quantum teleporter? Let me know in the comments below. Thanks for watching, and as always, keep questioning reality.